Hello, my name is Naima Jory, and before we get started, go Jackets! Last night's game was such a good one. Alright, anyway, Lab 4, Oscillations. The main purpose of this lab was to analyze the motion of a spring mass system with the mass oscillating in an arc. How did I do this? I used Tracker to track the observed position, and then GlowScript as the computational model which would predict the ideal motion. And I did this to determine whether the computational model would actually follow the energy principle. And the result was that the system's total energy remains constant at zero, thus demonstrating the energy principle. So what were the main physics principles used in this lab? First up, as always, we got Newton's second law, which states that the system's change in momentum is proportional to the net force applied. And here it is written out. Well, for our lab, we have a beautiful drawing of our spring mass system. We have on our mass the forces of the spring acting upwards and the force of gravity acting downwards. So we can write that as a net force is the force spring plus force gravity. Well, we can also expand this to write it in more detail too. Okay, next up is the energy principle, which states that the system's change in energy is the sum of the work done by the surroundings and thermal energy exchange with the surroundings. Here it is written out. Well, we have to define what our system and surroundings is before we can basically write this out. Our system in this case is the mass, the spring, and the earth, and our surroundings is basically everything else, but in this lab we're basically going to isolate the system, so there's no interactions with the surroundings. So that means the change in the energy of the system should be zero. And for our system, we're going to have kinetic potential spring energy and gravitational potential energy all equal to zero. And here's some more useful equations. Here's the short video that I used in my tracker analysis of the observed motion. The object's mass was 0.402 kilograms, the stretched length of the spring was 0.7 meters, the initial position was that, and the initial velocity of the mass was 0 meters per second since it was dropped from rest. The two graphs on the bottom is basically just plotting what's going on in the x and y direction over time. So before I can get started with the computational model, I have to find a couple initial conditions first. So first up, we got solving for the period. And what the period is, it's the time it takes to complete one whole cycle. So say spring starts here, one cycle, that's the period, the time it takes to do that. So how I did this was I looked at the graph for the motion in the y direction, found three different periods, and then took the average, and it became 1.5197 seconds. Now, since period is related to k as seen in the equation, I solved for the spring stiffness, and it turned out to be that. And then I was able to basically find the relaxed length of the spring. And that's all the initial conditions we need to know. All right, time to code. So first up, what I did was input all the initial conditions, and most of these were found through the observed tracker data. Next up, I inputted the spring length and direction and the system energies. Again, the spring length can be found by subtracting the relaxed length of the spring from the stretched length. And then for the energies, I used a formula for kinetic, gravitational, and spring potential energy, added them all together in order to get the initial energy of the system. All right, now for the chunkiest and most important part of the code, the while loop. And basically what's going on here is that we're iterating through each time step and calculating the change in energy. Well, how do I do this? I first calculated the gravitational and the spring force and ultimately the net force. And from previous labs, we know if we have the net force at each time step, we can find the velocity and the position of our mass. And using these quantities, we can find the kinetic and the potential energies of our system and ultimately the change in energy at each time step. All right, time for the results. So the animation on the left was generated by the code and it's showing what's going on in the computational versus the observed model. The two diagrams in the middle are showing what's going on graphically. It's showing the oscillating function. So what we can tell from this is that in the beginning of time, the two models tend to overlap, but as time goes on, they start deviating more and more. And the reason for this is that in reality, the system is not isolated from the surroundings. We have work being done on the system by like the drag force. Also, when I had to individually place each center of mass in tracker, it got pretty tedious by the 100th time, so I might not have placed it exactly at the center of mass each time, so please forgive me on that. Let's answer the big question. Is the energy principle satisfied? Well, let's think about it. In our model, we said there are no external forces acting on the system, so the change in energy should be zero. Well, looking at the graph, even though we do have different sources of energy, the change in energy is constantly at zero. So yes, the energy principle is satisfied. Last up, comparing oscillation periods in the x and y direction. The method I used to find both of these is the same as before, basically looking at the graph of the x and y motion, finding 3 consecutive periods for each, and then taking the average. And as we can see, the periods are different when you choose different directions. So ultimately, different directions produces deviations in the period, which ultimately affects the spring constant and the graphs. Thank you so much for your time and have a great day.